Think we'll go ahead and get started now. Hi there. My name is Zach Hoyle. I'm applications engineer here at SpinPo, which is the global distributor for the TurboTides software. And I wanted to welcome you to our TurboTides webinar on pump design. In addition to me, we've also got our managing director, Catherine Zhang, on the line. I think she's going to come on and say hi.
Hi, welcome to today's webinar. My name is Catherine Zhang. I'm the Managing Director of SpinPo. SpinPo is the global provider of the TurboTides. We are excited to bring together such a dynamic group of the attendees about the TurboTides. I hope you will find today's section informative and engaging. Hope you enjoy the session. Thank you.
Thanks, Catherine. We've also got Sean Lee, our Director of Engineering, on the line as well.
Hi, everyone. Good morning, good evening, and hope you enjoy today's webinar. And if you have any suggestion, questions, please feel free to ask us. Those all of us are welcome to help you anytime. Thank you.
That's right. Thank you, Sean. So this, as Sean mentioned, feel free to ask questions. I think we've got a Q&A tool on Zoom, and after the webinar is over, I'm going to be replying to those via email, as well as sending follow-ups and a recording of the webinar to you. So let's go ahead and get started here. TurboTides is the most easy to use and full-featured turbo machinery design software. The company was founded by Dr. Xuan Q, who is a turbine design expert who had used a lot of the products that are out there on the market and wanted to see something new to solve a lot of the long-standing problems with the typical tools with turbo machinery design. All the other products on the market are built off of work that was done a long time ago. And while this new TurboTides program is a much more modern, intuitive system and has an advanced program structure and interface. So what's special about TurboTides, as opposed to our competitors, is that every step of the design process is all contained within a single program, which can easily transfer data from one stage of the design process to the next. Each step in the design process has its own module, starting with the 1D module, then our 3D geometry module, CFD, FEA, and so on. And the data flow between each one of these is all managed by a separate central database, which also allows us to optimize and do full-featured multidisciplinary optimization. This program was developed much more recently than any of its competitors by a larger engineering team and was developed using more modern techniques in computer science. So for this reason, TurboTides can provide a much smoother workflow than our competitors, from 1D preliminary design, 3D geometry generation, automatic meshing through 3D CFD and FEA structural analysis. So furthermore, we also offer extensive support for the redesign and optimization and reuse of past designs, which we'll go into a little more. Although we are the new player in the industry, we work with a lot of large companies as well as small companies and startups. So why TurboTides? TurboTides has a very heavy emphasis on the ease of use and having a seamless and customizable workflow. So users don't really need to spend a lot of time in the TurboTides software to get a good pump design. They do not need to be experts in pump design or CFD in order to be successful users of the software. In addition to the ease of use in TurboTides, the designer also has much more options over how they want to modify, analyze, or optimize in the geometry. There are unique features for reverse engineering and model calibration, which save a ton of time in the design process. And we offer all these features as a single low price. Although some parts of the program can be priced out separately, the TurboTides software includes all these features with a much better value than what the competition can offer. Our competitors usually charge extra for when a customer might want to have some additional features, tools, or training, whereas SpinPo works with you on these and is known for having the best customer service in this industry. My job is to provide the same day or real-time customer technical support. And so that's my role on this team. For trials and new customers, we offer free remote training sessions and have recorded tutorials and documents. And it doesn't really take a lot of time to get users trained on this software and get them started. So all these advantages kind of mean that our customers can design pumps much easier and much more efficiently with TurboTides. So as you'll see in the demonstration, the workflow is very simple, although this chart here shows that we have a lot of options as far as how the user wants to work with TurboTides or interface with external tools. The way that this typically starts is that you design from scratch using the 1D design wizard. Then you're able to make a performance map in the 1D analysis mode. Then the user can make changes to the design or change the performance map to their preference. And then the 3D geometry can be generated with a single mouse click. So at that point, the user has a wide range of things they can do to modify the geometry, or they can move straight to CFD to get a prediction of performance, which they can use either our CFD or an external tool. And this whole process in TurboTides can take a very short amount of time to predict performance and to get a good pump design. The user does not need to be an expert or understand everything about CFD or pump design in order to use this and to get started. So with TurboTides, we have the capability of designing just about any type of turbo pump you can think of, axial, radial, and mixed flow machines. We can model multi-stage machines with as many stages as you want. And in TurboTides, you can design special types of blades like radial element or axial element blades. With the software, you can design across the entire spectrum of specific speed, from really low specific speed pumps up to really high, and can model double suction pumps, multi-stage pumps. So in addition to just being able to design different types of impellers, we also have a very full-featured tools for designing auxiliary components, like volutes, veined and veinless diffusers, inlet chambers, including symmetric or asymmetric inlet chambers for double suction pumps like we see down here. The 1D and 3D can design any of these, as well as inducers. We also have tools for modeling secondary flow paths or seals, and for modeling the mechanical geometry as well, including things like the back face, adding fillets, the bore and shroud geometry, and so on. So one of the things that gets pump designers excited to switch to TurboTides is our focus on making use of legacy designs and test data, as many pump designers have previous designs that they want to use as a starting point for a new design or to improve the existing design. The 3D CAD import tool gives you the capability to bring in an existing CAD file and can automatically converts it into a parametric model with editable distributions for the blade angle, thickness, and the flow path curve distributions, which you can then optimize on. It's a very easy to learn tool. And furthermore, in addition to the CAD model, if the user has test data to go along with that design, like they've already done some tests on this, they have some idea of how it's going to perform, then our unique 1D data reduction tool can be used to calibrate the 1D model, so the user can then use the fast 1D model to accurately assess changes to the operating condition or geometry without having to do additional tests or CFD. That data reduction feature we'll go through during the demonstration in a little bit here. So arguably the most unique feature that we have in this program is the 3D AI optimizer. It's powered by the most advanced and fastest multivariable AI optimization tool that's out there. It's called Oasis. It was made by this company called Empower Operations in Canada. With this 3D optimizer tool that we've integrated into TurboTides, the user can set an objective like maximizing efficiency. They can set the variables, things like the blade angles, the thicknesses. It can set constraints over things like the pressure ratio or the head rise. And the optimizer will automatically make modifications to the variables to achieve the objective using its AI optimizer. We can use either FEA or CFD analysis to drive the optimization. So you can do things like minimize the maximum stress or tune the mode shapes. So depending on the number of variables, it doesn't take much time to get an improved design. It's a lot faster than any other optimizer that's out there, according to our experience. And the optimizer also can be multi-objective or multidisciplinary, meaning that you can optimize on both FEA and CFD results at the same time, like minimizing max stress while also trying to maximize the efficiency of the machine. Or you can optimize on multiple operating conditions. So to summarize some of the big differences between TurboTides and its competitors, you're able to make efficient pump designs and improve existing ones very quickly, and you have a lot more options in the design process. And that's the overall main point here. TurboTides can model a very wide range of different types of pump designs, and unlike a lot of our competitors, you can model any additional component for no extra charge. No other software offers the workflow options and customizability that we do while still being easy to use. Our competitors are usually either easy to use or very detailed and complicated, while we offer a very unique combination of both of those things. Our 3D CAD import is the most accurate and robust tool for importing and working with existing geometries, and our competitors don't really come close to what we can offer here in terms of the capability. The AI optimization tool that we have, no other competitor offers this kind of multidisciplinary AI optimization powered by this extremely powerful algorithm. SpinPo can also offer new features as conditions of sale with the purchase of TurboTides, which is pretty unique in that our competitors usually do not offer this type of service and charge quite a lot of extra money in order to incorporate any kind of new features. So let's go through a demonstration here. We're going to start by designing a radial pump, although later on I'm going to show you some examples of mixed flow and axial pumps that we can design as well. So, excuse me, on the left side of the screen, when you open up the TurboTides program, you see the program modules, the cycle modeling tool, our 1D mean line module, 3D geometry, CFD, and FEA. But to create a new machine, we click on this new machine button, and we have the different types of machines we can create in TurboTides: axial, radial, or mixed flow machines of compressors, pumps, turbines, or fans. In this case, we'll choose a radial pump. And to get a new design started in TurboTides, we're going to be going to this design wizard, which is a very quick and easy step-by-step process to have TurboTides define a design for you. Starting with where we select the fluid, where water's the default, but we have a big database of different types of fluids that you can create a mixture of or define using by entering in the properties of that fluid. For now, we'll use water. And then we enter in the design condition, where this is the operating condition at the design point. We can provide these operating conditions at the design point using whatever units that we want. So if you are used to using a different unit, you could either change the unit setting or just enter it in this table, however way you want. You can add as many stages or have this machine be as many stages as you want. And then we select what type of design mode we're going to be using. The conventional design mode uses well-tested and accredited correlations to predict the loss, deviation, and blockage to predict the efficiency and the performance of the machine. Whereas this fast design mode is a little bit different. This one uses correlations of specific speed to predict the efficiency, although the user has the option to input their own known efficiency value, as some pump designers like to provide this information themselves. And it's also a good alternative for very low specific speed pumps where the standard conventional correlations can struggle. So for now, we'll use the standard design mode, and then we select what type of components we want to have on this machine, what's going to be included on it. In this case, we are going to be including a volute, although we can include vane diffusers, inlet chambers, inducers, or any type of exit component that we want. And after we run the solver, we'll get a preliminary design. And at this performance table on this side here, we have a customizable list of different properties that we can pull up of the predictions for. We have things like the NPSHA and NPSHR, which is helpful for pumps. So this preliminary design that we have here, we can apply constraints to it at this point by going to the configuration windows for any one of these components in the machine. We can double click on any one of the components to get to that window, and this is where we can apply some constraints over the geometry if we want to. So if the user wants to define a constraint over the hub or the tip radius, they can change these options, which change how the inlet hub and inlet tip radius are defined. Similarly, for the outlet radius and outlet width, if you have those specified, or if you want to use our standard correlations, you can. But we'll, in this case, just use these standard ones, although we do have the option to have the user input either the exit blade angle or the exit diameter to create their design, although we'll just use this standard option here for now. The geometry tab, we have some additional options over modifying the geometry. But after, just to show you an example of the type of constraints that we can apply, let's say that we want to make this machine a little bit shorter. We can reduce the axial length. And when we click OK and run the solver, we'll get a new design that's generated, accounting for that constraint, but still meeting the required head and still having the required specifications. At any point during this process, we can add additional components or remove components like inducers, inlet guide vanes, an inlet chamber. For instance, we could add an inducer, and when we run the solver again, it will regenerate the design and include and design the inducer as well. You can see our NPSHR has gone down a bit as a result of incorporating that inducer. And we can go back to what we had before just by removing that again. So it's a good idea to model the effect of leakage around the wheel. And the way that we can do that is by entering the configuration windows for either the front or the rear leakage path. And we have options for changing the gap, but it's a good idea to add at least one seal if you're planning on modeling this accurately, as this will, after you add a seal, then it'll incorporate the effects of the leakage into the calculation. So we can, in this case, we'll just do a simple flat seal. We can enter in the properties for that, but after we click OK and run the design, then we'll get a revised design with the effect of the leakage incorporated. So we've generated a preliminary design here, but let's say that we want to make some more in detail adjustments to the geometry or predict how it might perform at different conditions. This is where you'd go and you'd try to change, and you can change the solver setting. Up until this point, we've been demonstrating the design mode, which will regenerate the design every time you run the solver to meet, and it regenerates the geometry to meet the required head. Whereas if we switch to analysis mode, it will predict performance of whatever geometry you impose on the solver. So now you can make more in detail adjustments and see how that might affect the performance of the machine and the head rise and efficiency. This can also be used for predicting performance of the machine at different conditions. Like in this case, we can we can make a performance map, which in this case, I'll just use the standard map range, but I can enter in as many points for the mass flow rate lines and the RPM lines that we want. And when we run the solver, it will predict performance using this default range of mass flow rate points, and will give us prediction of performance at each of these 21 conditions. So after this solves, we'll get a couple performance maps which show up. These performance maps are customizable, so we can view whatever X and Y property we want from inlet to outlet and chart that instead at each one of these operating conditions. So this analysis mode, at this point, you could go to the configuration windows, and you can see that we have a lot more options over how we can modify the geometry. We can directly change any one of these parameters and see how it might affect the performance. Under the blade tab, we have a lot more options over how we modify the blades under this main blade setup. We can change the leading and trailing edge blade angles. We also have this 3D blade editor within the 1D module, which allows you to preview a 3D view of the geometry here. You can modify the beta plot thickness of conformal mapping or the meridional plot to create a revised blade geometry. So it's kind of an advanced feature here, but we have the point is we have lots of options over how we can modify that geometry. So for last bit of this here, I want to show you that we can predict the axial thrust. Very simple. After we've accurately modeled we've modeled these seals as accurately as we can then run the axial thrust solver, which will predict the axial thrust at each one of these 21 points. So after this calculates, we'll have our predictions of the axial thrust, and we can view those on this axial thrust table here. So there's always more we can do in this 1D module. There's optimizers, there's database features, but for now we'll move on to geometry to keep this thing rolling. And to generate the 3D geometry, all we need to do is to press this import from 1D button. When we click on that, it will convert the 1D geometry into 3D geometry. It'll convert all those 1D parameters into hub to shroud and inlet to outlet distributions of these parameters that you can then modify using these Bezier distributions. We have 4 windows that come up when we open up the geometry module. We have this 3D main view that we can use to preview the blade's geometry and look at the machine. Flow path curves, which is an editable distribution of the hub and shroud lines, as well as the leading and trailing edges, the blade beta plot, which is the blade angles, and then blade thickness. One of the useful features that we have here is that we have this 2D hub to shroud solver tool. This is a streamlined curvature solver with a customizable mesh. We can run this hub to shroud solver across an entire map if we want, but this solver provides a 2D performance prediction as a contour plot as well as a line plot. We can view any one of these properties, whether it's a flow speed, pressure, Mach number. Blade loading is a useful one, as the blade loading tracks the pressure difference between the pressure and suction sides of the blades and can be helpful for predicting potential flow separation. So to illustrate the way that we make changes in the geometry module, let's increase the outlet blade angle here. And the way that we do that is by using these editable distributions for the hub, the mean, and the tip, where the hub is represented by this 0% line, the tip is 100%, and we can make modifications to those distributions, click apply, and then that change will be applied to our model. Similarly, we can apply changes to the flow path curves or modify the scheme by which we can these curves are made. Like we can change the Bezier distribution, we can import points from this, export points. But after we make a change, we right click and click apply, and again that change is applied to our model. And we can run the 2D solver again and get an updated prediction of performance with these with this updated geometry. And we have a higher outlet pressure now, and we have a higher blade loading now as a result of increasing that outlet blade angle. However, you can undo any changes that you make in this module. Very easy to do. All you have to do is just press this undo button twice, and we're back to what we had previously with our blade beta and flow path curve plots. Another really useful aspect of this geometry module is that we have the ability to change the dimensions of the machine similar to the 1D module. Where, for instance, if we wanted to increase one of the dimensions like the inlet width, we can increase the inlet width of both the inlet and the impeller, and we get a wider inlet here. And we right click and click apply, similar to those other plots. And we get our updated geometry, which again, it's very easy to go back if you made a mistake or if you want to change something. So there are a lot of options for modifying the impeller, not just these windows that we see here, but a lot of those options for modifying the impeller are in this blade tab, like row manipulation, where you can change a number of blades and some other properties. This leading and trailing edge aspect ratio plot is where we could change the shape of the leading and trailing edges, which by default are sheared at the trailing edge, rounded at the leading edge. We can change the aspect ratio of these rounded edges using either constant or variable aspect ratio from hub to shroud. We can pull up a preview of the shape of those leading and trailing edges. And when we click OK, then that change will be applied to our model. We'll see that we have a larger aspect ratio, sharper leading edge now. Some of the other modifications for modifying the impeller are going to be in the Add Remove Material tab here, where we can perform a flow cut, which will reduce the mass flow rate of this machine by moving the maximum mass flow rate of this machine, rather, by moving the shroud down closer to the hub by either a percentage that you can define, a distance, an offset, or an editable distribution. So if you want to draw your new shroud curve as opposed to creating it using this flow path cut, you can do it this way. So, but for now, we'll just do this simple 10% flow cut. It takes a little bit of time to load this, as it has to regenerate the blade, the distributions. So while that's loading, I wanted to show you a multi-stage case here. I think I pulled up the wrong case, sorry. This is an example of a radial pump that we created in TurboTides, a multi-stage one. This is an example of the type of multi-stage machines we can create. Similarly, we can create mixed flow pumps, not just the radial pumps. This is a multi-stage mixed flow pump that we created. So going back to here, we've done this flow cut. It has reduced the maximum flow rate of this machine. We also have the opposite of this flow cut, which is flow extend. So this is where if you want to move the shroud farther out to increase the maximum mass flow rate of that machine. So we've also got operations like diameter trim. If we wanted to reduce the head of this machine, reduce the outlet pressure, this is one convenient way to do that. The cut can also be asymmetric, and we can do this at an angle like this if we wanted to. Similarly, we've got the opposite of that as well, where we can extend the diameter outwards. Where if we preview this, this is a useful tool for making the head of the machine larger and increasing the maximum pressure of the machine. There are other operations here like swept leading edge, which will trim away from the leading edge. Double suction will convert the machine into a double suction. So we'll get a mirror image of the other of this impeller on the other side. Although we need to change our volute and our diffuser here. Pretty easy to convert that. We can also scale the machine up or down by whatever factor that we want. If we want to make it larger, we have flank milling for converting the machine to a flank millable geometry. So those are just a preview of some of the options that we have for modifying the blades. But to go through a little bit of the options that we have for modifying additional components, let's look at what we can do to the volute. The volute editing tools in TurboTides, we think that this is really the best volute editing tool in the industry. You can make just about any volute shape that you want. It's very full-featured and easy to use. Starting with the cross-section shapes that we can achieve, the Bezier is convenient because it is an editable distribution that we can modify. However, we can constrain those changes to be symmetric. But there are other cross-section shapes that we have, like elliptic. We can have this be hanging on the left or the right, or be symmetric. We have split Bezier double volutes, which split the flow in the middle of the volute, twin Bezier, rectangular volutes. And we also have this, and of course, we have the option for the Bezier. So, sorry, I didn't mean to exit out of that, but going to some of the other options that we have here within the exit pipe window, we can shape this exit pipe however we want. And we can make whatever crazy shape we want here, and we can constrain this so that the outlet is actually in the radial. It's a radially oriented outlet. We can implement things like early turning angle. We have options for modifying the top curve here in addition to this, the curve representing the middle of the exit pipe. But after making that change, we can click OK and we see our updated volute. But there's some other options I wanted to show you here, like edit sections. This one allows you to make modifications to any one of the sections in the volute from 0 to 360 degrees. And you can make, this is how you can achieve just about any distribution that you want. Although we do have the option of implementing whatever area distribution of this volute using an area plot like this. We also have this, the tongue tool, where if we want to implement a fillet between the inlet of the scroll and the exit pipe, we can turn on this tongue, where the tongue can be a editable distribution. We can make the shape of this curve whatever we want. We can change the tongue radius and the start angle. Well, we'll just stick with what we have here. So the geometry that we have here, before you actually export that geometry, it's probably a good idea to model a mechanical geometry as best as you can. And what that means is the back face, the shroud shape, the bore shape. And within this window, we have a lot of options. So we have where we modify those. We can also add fillets onto either the hub or the shroud. This parametric disc tool is nice because you can define this back face using parameters, which can be optimized on in the optimizer to reduce max stress or to achieve a different objective. We have options in the bore tab where we can modify how the bore is defined or implement counter bores. Similarly, under the shroud window, we can do a parametric shroud or define a fillet on the shroud if we want. We'll just stick with what we have here. It always takes a little bit of time to generate the fillets, as we recommend keeping this as the last thing that you do before you export the model. Although there's one more thing that I want to do now that we've added on these fillets, as you can see here, and that is I wanted to model the secondary flow path. The secondary flow path, we've already added one in from importing from 1D, but just to show you this tool, let's remove what we had previously. And to add a leakage flow path, we go to this Add Leakage Flow Path tool, and we can have this be either a front seal or a front leakage path or a rear leakage path. And this leakage path will automatically conform to whatever shape of the back face that you have. So we can change the size of this however we want, click OK, and then we'll have this distribution, which is now editable, added on our flow path curves and on our model. If we look at the model here, you can see this cutaway region of the impeller. Next thing that we can add is a seal onto this leakage path, as it's just kind of a path at this point. There's no seal, so we have this seal geometry tool where you can change the seal location from inlet to outlet. You can change the number of teeth if you want to make a labyrinth seal or make a flat seal just by making a very wide tooth. You can change the pitch, width, clearance, the side on which these seals are oriented, and you can add that to the leakage and it'll be included on in whatever CFD mesh you create or the geometry that you export. Speaking of exporting and importing geometries, there are a ton of options over how the geometry is imported. We don't have time to go through those today, but I can show you those on a separate demonstration, how we can do the import from CAD file. We can import volutes. We can import from text files, blade coordinates, CSV files, from TurboGrid if you have existing geometries hanging out there. We can also export geometries a number of different ways, starting with the CAD file, which can be either a solid model, a surface model, or we can just export curves for any one of the components that we want here. And we can choose what it is that we're exporting with this window. And also we can choose the format. We also allow you to export to TurboGrid, as we do not force you to use our CFD. We like our CFD here, but it's not, we're not going to force you to use it. So those are the options that we have for exporting and importing. Don't have time to go through all of them, but just to move on to the next step here, our CFD module is a very simple, easy to use tool where all you need to do to generate the CFD setup is to press this import case from geometry window, where we have some options over how we can define the mesh, although we have expert controls for that as well. But while this is generated, I wanted to show you a axial pump case as well. While that mesh is generating, not only is it generating the see if I can go back there. It's not only is it generating the mesh, but it's also generating the boundary conditions, all the operating conditions. So all you really need to do is to press the run solver button. This is an axial pump case that we have. Just an example that I pulled together. We have a slightly different tools for modifying axial geometries where we can define the geometry using knockup profiles, using a number of different types of airfoil parameters that we can choose from. We can define the blades using beta, camber line, and thickness profiles, and similar to the other pump types, we can run the 2D solver, make modifications however we want. But our mesh is generated over here, so we can see our preliminary mesh. We can always refine it further, but this will probably be okay for now. The setup for this case is automatically generated using the 1D parameters, but we can change these operating conditions. So if we want to see if we wanted to change the boundary outlet boundary condition from exit flow rate to exit static pressure, then you can do that, which can be helpful while you're making the CFD map. We have additional controls for how the CFD solver itself works. As far as the turbulence model, the multi-phase, whether or not we want to include cavitation, which is a good idea. and some other options over how we work with the CFD solver. But it's meant to be very simple and easy to set up, where you don't really need to be an expert. You just need to follow the main recommendations. So it doesn't take a lot of time to solve CFD in TurboTides. We've got we don't force you to use our CFD. We understand that that CFX or another program is a well-entrenched service, so there isn't really we're not really trying to compete with those. Our tools are we focus on the turbo machinery design, and CFD is our users use it a lot. It's very accurate. It performs well, just as well as CFX, but we don't force you to use it either. So that's why we have these other interfacing options. But this is a completed CFD map for this case that I already did. We have the CFD results. We can view a number of different ways, including these contour, vector, streamline, iso contours, or RZ plane contours. We don't have enough time to go through all of these, but we have line plots as well, where we can view the flow properties of lots of different types, from inlet to outlet and from hub to shroud. So we also kind of moving on to one of the most unique aspects, and kind of the last part of this demo, is the data reduction. So this is probably the most powerful and unique aspect of this program, where you can use these CFD results that we already have here to go back and calibrate our 1D, and then use the 1D model, which will now be accurate after calibrating, to make adjustments and not have to do time-consuming CFD. So 1D is very useful in turbo machinery design, as it allows you to quickly predict performance of the machine under different conditions. CFD takes a while, testing is really expensive, but 1D models take seconds. But the challenge with using 1D models in performance prediction, of course, is that it's not always accurate. And that's because the 1D model correlations are empirical correlations that try to predict a 3D flow field using 1D parameters, which by its nature is not going to be perfectly accurate. However, by using test data, TurboTides is uniquely able to make the 1D much more accurate by modifying the loss coefficients, deviation, and the blockage such that the 1D model matches the test data, and then you can use the 1D model to accurately predict how that machine might perform, just as accurate or comparable accuracy to what you might get from CFD or doing a test. So using this tool, available only through TurboTides, instead of doing tons of CFD, simulations or expensive testing to get a design you want, you can use the 1D modeling. It's a much more powerful data reduction and 1D calibration tool. So although this data reduction is most often used for an imported design, when you're starting from an existing design that you have test data from, we can also use CFD results to calibrate the model. So I wanted to demonstrate that here by exporting this completed CFD to a data reduction table. We can name that however we want, but it'll export the most important parameters for the performance, which it'll export a CSV file. That's how you create a test data file in TurboTides. You have on the left side the variables, and then each one of the operating condition points that you're trying to calibrate using. You can provide additional properties, like if you have a varying inlet pressure, but the solver assumes that that's the same for each one of these points. So going back to our 1D here, it's a good idea to export to 1D before we do the data reduction to make sure that the geometry in the 1D perfectly matches what we did in CFD. Then we can feed in this test data by going to this data reduction tool and importing from files this file that we just created, which is this one right here. And then we select the variables of this table that we're trying to calibrate, which we really only need these four, as the inlet pressure is defined in the operating conditions. And it's the same for every one of these points in CFD. So if we press this run solver button here, it will go through each one of these points point by point to modify the loss deviation, the loss coefficient, the deviation, and the blockage iteratively until the performance prediction in TurboTides perfectly matches with the test data. After it goes through every one of those points and creates this matrix of loss deviation and blockage coefficients, then the TurboTides will have a calibrated model, and then we can accurately use this 1D model to predict how this machine might perform at different conditions, even outside of the CFD data that we have. So we see this line on our 1D plot now, but to confirm the model is calibrated, I want to change the x-axis of this plot and overlay the test data that we just exported. And when we look at the difference, you can see that these two lines are right on top of each other, showing that the performance prediction in TurboTides now perfectly matches the test data, meaning that the model is now calibrated, and we can test this calibrated model similar to how we might test a real machine. So now I think it's a good idea to save as, and we can call this whatever we want. I'd call this calibrated. And now at this point, we can predict performance of this machine using the analysis mode. Similar to what we did before, we're going to make a performance map and see how this machine might perform at different conditions, where I already have a set range of points in mind for this. So I'm going to set up this map real quick. We can generate this map this way, click OK. And now when we run the solver, it will give us a prediction of performance using this calibrated model. And the thing that's most important about this is that if you have enough points in your CFD map or your test data, that you can be confident that the performance prediction of the calibrated model is accurate, even after you make even if you make some minor modifications to the geometry, or you make modifications to the machine's operating condition, or even its fluid type. So now that this is completed, if we look at this performance map over here in this overlay, you can see it's still matching the original test data, only now it's extrapolating using that test data to see how this might perform at conditions outside of the test data at lower flow rates as well as at different RPMs. So with the calibrated model, not only can you change RPMs and operating conditions, you can change the fluid type and it'll stay accurate. But it's a good idea to save what we have here before we make any kind of modifications to this model. Call this analysis, as this is in analysis mode. So let's say, for example, I want to increase the flow capacity of this machine. I want to move the map to the right a little bit. Well, we can use this calibrated model and make some modifications to the geometry. And even though we're making modifications to the geometry, this performance prediction should still stay accurate, and will still give us a useful prediction of performance. Okay, so we run the solver again, and then we'll get an updated prediction of performance with this updated geometry. So up until this point, in order to get this kind of updated performance prediction, you would have had to do a bunch more CFD or do a bunch of expensive testing. And those are much less convenient than using a calibrated 1D model. Our customers have used this successfully in industrial applications for compressors, turbines, and pumps. This is a well-tested method which has been used for real machines. So after we've made those modifications, you can see the effect of moving the map to the right a little bit here. So that kind of updated performance prediction, the overall point of data reduction is that it's meant to save time in the design and revision process. It might seem kind of hard to believe that a calibrated model could keep accurate performance predictions even though we're working on 1D. Well, we've done some work to confirm and provide some evidence of that. Where what we did in this case was we had a design which we had test data for. And we calibrated the model, and then we compared the calibrated model's prediction of performance to a CFD simulation that reflects those same changes. So we're going to see how a calibrated model, after changing the fluid type to helium and scaling the whole machine up, might perform compared to a CFD simulation. And you can see that there's not much difference there at all. Even after making more drastic modifications, like changing from air to propane and scaling the whole machine down drastically, we still see a very a good agreement in the performance predictions. We can change the geometry as well, doing things like changing the IGV setting angle or changing blade angles can be accurate as well. Even doing something really drastic like flow cut, which is going to really change the frictional flow through the machine, is going to affect what losses take over. However, we're still getting a useful prediction of performance, even though we are making a drastic change to the geometry here. So the point is that by using this, you can save time in the overall design and revision process. So to close this presentation out here, to go over some of the strengths of this TurboTides and team and with SpinPo, the TurboTides development team has a very large and robust development team, which gives us a much faster pace of development than our competitors. SpinPo has the most responsive customer support in the business. That's my job. We can provide support from the development team on new features and functions, and we provide a lot more training and help than the average competitor. So to summarize, we have an integrated turbo machinery design system that covers all types of turbo machinery, but is especially advantageous for pumps. It has a very smooth workflow on a single platform, which facilitates almost all the design process within this single program. We have unique reverse engineering and CAD import, legacy design, and data features which enable faster development time. And we have what we think is the best in-class value. So to close us out here, thanks so much for attending this webinar. There are a number of different ways you can contact us. I've listed my contact information on here, but I'll also be providing in the follow-up email to everyone who signed up, Catherine and Sean's contact information, so you can contact them with any questions, but you can also reach out to me on this email that I've listed here. You can get a hold of us to schedule a full demonstration or to see how this and to show how this might perform, show how the program works for your application. Remember that we offer free remote training sessions to trial customers, and so that'll conclude this. Thank you so much for attending this webinar.
So any questions from the audience?
So it doesn't look like we allowed the attendees to talk. I apologize for that, but if you have any questions, please contact me via email, and I'll be sure to respond to those right away today. So thank you all for attending, and have a nice rest of your day.